and how to interpret them. We'll learn a little bit more about the makeup of the circuits inside there, not to understand how they do it, but why these data sheets are the way they are. So first of all, we're going to deal with TTL, which is what we're predominantly dealing with this semester. And what does TTL stand for? And what does that mean, TTL, as far as the makeup of the circuit? Well, the first one gives you what you input on. So this is what you input on. And your second one tells you what we output on. So TTL would be we input on transistors and we output on transistors. That makes sense? So if I was to come over here and do this, this was one of the first logics, guys. This would be so this, if this was out and this was in, this would be a logic we call DTL, which means I'm inputting on what? Diodes, and I'm outputting on what? On a transistor. So that was a lot. We had RTL, which means we input on resistors, we output on transistors. But the predominant logic is TTL now. But you might run into some of these. And then they would take this. We could wire the circuit up, but sooner or later, if the circuit was around a long time, they would integrate this into a single package, right? You understand? And all I'd see A, B, and X or something like that, right, when I set it up. But this would be called what we call DTL, which means we input on what? Diodes and output on transistors. So TTL means somehow we come up with a circuit where I can input on transistors and output on transistors. We're going to look at a 2-input NAND gate. We're going to look at multi-emitter transistors. We're going to look at what we call a totem pole output. And the high logic level and the low logic level. And what we're going to look at the data sheets, you're going to see some of them's got typical. Then some of them usually has minimum and maximum. So this is the basic makeup of a NAND gate, TTL NAND gate. And some of y'all are running into this little diode right there right off the bat. And this is what we talked about. That diode is in there. If the input ever goes negative, then the diode right there would forward bias. And what that does, it prevents you from screwing up your logic. So some of y'all, when you did your triangle wave, instead of a triangle wave, if this was 0, what you did is you saw this. Because what was happening is that you didn't put a DC offset on it, and it was trying to put AC into the gate. And what was happening at 0.7 of a volt, that diode turned off and clipped off the negative alternation. Now, luckily, if it would have been a power source, it would have wiped your die out. It would have wiped that diode out. But luckily, your function generator, if you look at the output, it says 50 ohms. So that means it actually outputs to a 50 ohm resistor. So that means when you came over here and shorted that thing out, it didn't hurt the function generator. But you got to be real careful on true life in that if you ever make this gate go negative and you don't have you got a true power source, you could wipe out those diodes. Now, the way this thing works, and whether you really understand it or not, is that if any one of these inputs right here goes to a low, this is an NPN transistor, which we've already talked about a little bit. NPN. And what we're doing is we're looking at this. So I've got the base connected to plus through that resistor. And so when I come over here and put that 0 right there, and it's not a 0, it's actually a ground, right, or a common. People want to see a 0 as a nothing because you're not thinking about logic. You're thinking about if I've got $0 in my pocket, I got no dollars, right? You understand? But in logic, a 0 is going to be a voltage level. It's not going to be a nothing, right? It's not going to be a nothing in my pocket. It's a voltage level at 0. So what happens when this goes to a 0, I got a positive, over here I've got a negative, this guy right here turns on, and it saturates, and this negative comes flying through and sets right there. No, it sets on the base of this transistor. That transistor right there is an NPN transistor. I don't have a P on the base, so this transistor right here turns off. So if this guy right here is turned off, there's no way in the world I can get current over here to this base. There's no way in the world I can get current over to this base to turn it on. So that transistor right there turns off. Now here comes the positive right here. Comes over here. There's a positive. There's P. This is my output. So this guy right here would turn on, and it would come on, and it would pass this through, and the output would go up to around 3.4 volts. Now, why 3.4 volts is over here. I'm putting +5. We lose 7/10 here. We lose 7/10 there. So that's why we'll never get the 5 volts out. And then plus we feed it through a resistor. So when this input went low, the output did what? Went high. So if we call that A, B, so A is low. B, we'll put a high right there, which means this guy's not forward biased. So that would be a 0, and the output went to a 1. And then, of course, now we can do the same thing with the other one. So if either one of these guys right here if I put a 0 on either one of those guys, that first guy turns on. If this guy's on, this guy here's what? Off. If this guy's off, this is off, and that's on. So if this guy right here is off, if this is off, this one's on, right? Does that make sense now? So any low over here, any low will give me a what? A high. I'll get to you in a minute. Any low will give me a high, which is the same as that guy right there. So if I bring this right here to a low, now this emitter is forward biased. This emitter right here is not biased, right? This transistor turns on. That brings that 0 over here. Turns this guy here what? Off. If those guys off, we can't get base current here. This guy right here turns off, and this guy right here turns on. That allows the output to go to a 1. And of course, the same thing is going to be true if I put T0. Oops. So to turn this guy here on, if I come over here and put a 1 right there, now this guy here is not biased, right? You understand that? Yes or no? Because this is a what? This is an NPN. So on an NPN, by the way, on TTL is pretty neat. So a 1 is equal to at least what? We've already talked about that. Oh, sorry. Yeah, I don't know why it's clipping me. So on TTL, a 1, on TTL, a 1 is equal to at least what? We said 2.4 volts. Actually, it's less than that. And a 0 would be equal to million, not ohms. So when I put this 1 over here, I got to have at least 2.4 volts. Actually, it's not that. It's a lot better than that. We'll look at that. So if I come over here and this goes above 2 volts, this guy right here is going to turn off. This guy here is going to turn off. If this guy turns off, that means this guy here turns off. Now this guy can pick it up. It's hard to see through here. They'll turn this guy here on, right? Now when that guy turns on, what's going to happen? Now we can get current to this guy, which will turn this guy here on. Now why does that guy turn off? Well, what happens is this guy turns on. So that means I would have 0.7 volts right there. You understand that? This guy turns on and saturate. It almost drops no volts. That puts 0.7 volts right there. This guy needs 0.7 right here and 0.7 right there. So it needs at least 1.4 volts to turn on. All we're giving it is what? 0.7. So what would it do? It would turn off. That's going to connect the output to ground, so the output would go to 0. Now this is called a totem pole output because we got the two transistors stacked on top of each other. Q3 gives us the high, Q4 gives us the low. They are never on at the same time. So if I turn Q3 on, the output goes high. If it turns Q4 on, the output goes low. Everybody understand that? That makes sense. So if I put all highs over here, the output went low. So this is the diagram of a NAND gate. And that's called a totem pole output. We wipe out this guy right here a lot because this guy here is not protected. This guy right here is hard to wipe out if you screw up because it's protected by a resistor. So that means if you come over here and you put a true plus 5 volts on here by accident and you turn Q4 on, you got a short circuit and Q4 is lost. It's gone just like that. Now what would be the results? Well, the guy could output a high, but he couldn't output a what? He couldn't output a low. So the output would go to an invalid state. So when I come over here and turn this thing on, we're going to put a 0 right there, right? And we're going to have a current flow. So we're going to have base current. And so we'll see, okay, how much will that right there draw, right? You understand? So somewhere in your data sheet, it talks about input current, what an input draws. Now, if this was to go to plus 5 volts, and this right here was sitting at plus 5 volts, then this guy would not be forward biased at all. It would be flat off. There would be no difference in potential. You wouldn't have current flow, right? You understand that? Yes or no? But if this thing right here dropped down to 4.3 volts, or let's say 4.2, then this is more negative than that, and we would have current flow. So that means it's going to be a high. So we're going to have an input current for a maximum input current for a high, because a high can be anything between 2.4 volts all the way to 5 volts. So 2.4 volts, we would have a lot higher current flow through the thing than we would if we had 5 volts. But it's not going to be enough current to turn this guy here on fully and turn this guy. So this guy's looking at 0.7, so that's 1.4 volts. So if it gets below 1.4 volts, this guy right here should turn on. And then if it gets above 1.4 volts, that guy right there should turn off, I think, if I'm looking right. Might have that a little wrong. So when we look at these currents, we can see a high on the input is going to pull current, but it's going to be very, very low, right? Your low is going to require a lot of current because that turns the transistor on, a lot more current. Another term, and this will pop into play, by the way, when you get into PLCs. And it took me a little while, even myself, to understand what's going on. So, and this was a long time ago, guys. So, when you come over here, and this output right here turns off, and this output right here turns on, that means I've got something out here, right? You understand? I've got something out here that this guy right here is feeding. So current flow would be what? So let's come over here and output this into something like this. This would be a load. So I'm going to put plus 5 volts right there. So here I'm providing the ground. So what's it looking for? It's looking for 5 volts. Does it have 5 volts out there? Sure, right? So the current flow would come flying. It would come out of the gate, going in this direction. It would come up, and it's not looking for this. It's looking for what? It's looking for that guy, and the current flow would be that way. Everybody okay? That makes sense. So if I'm outputting a high, so a low, the current flow was this way, right? Right? So if I'm outputting a high, then this guy's going to turn on, and this is outputting a positive voltage now, and the positive voltage is looking for a ground, right? You understand? So which way would the current flow be? So how would the current flow? Anybody got any idea? It's going to come up this way and go this way up through here, looking for 5 volts. So when the output is a low, the current is flowing out of the gate. When the output is a high, the current flow is into the gate. Well, what we're doing is when we we either got one guy forward biased and one guy not, or one guy. So what's happening is either when I output a high, so on this thing, Q3 is going to go. It's going to turn on when my gate is outputting a what? A high, and Q4 is going to turn on when my gate is outputting a what? A low. So when it outputs a low, it's looking for 5 volts. When it's outputting a high, it's looking for a ground, right? You understand that? So a lot of data sheets I would get into when it started talking about the characteristics of the gate, and it called it AC characteristics. And I couldn't understand that. I said, how can it be AC? How can it be AC when I've got nothing but a 5 volt supply? And then I realized that when you're outputting a low, current flow is out of the gate. When you're outputting a high, current flow is what? Is into the gate, into the output. We're not talking about voltages and not voltages. We're talking about the direction of current flow. So this current right here, by the way, so this guy right here came up with the name of call-in sourcing. So when we say the gate is sourcing, we mean it's outputting a what? It's outputting a high. When this guy turns on and the gate comes out, this is referred to as sinking. So we have what we call a sourcing current and a sinking current. So sourcing means the current flow is into the gate. Sinking means the current flows out. So if the gate is outputting a low, we say it's sinking. If the gate is outputting a high, we say it's sourcing. Does that make sense? Guess where you're going to run into that again? You're going to run into that in PLCs, especially when you when you get in how to connect the outputs. So I can go over there into A200 and I can go over to one of the PLCs and it's got a module up there and it says it's a syncing module. So that means it's true when it's low, right? Does that make sense? So we have a syncing sourcing current. So syncing means where the gate is outputting a watt. A low. Sourcing means it's outputting a high. The high is easy to understand because it's providing the source, right? You understand that? It's just that syncing that's a little weird. And you're going to run into this again, especially in PLCs. In fact, you'll run into that if you take intro to PLCs. We'll talk about that and you'll have to draw some inputs and outputs. So source current, it's called source current, sync current, low-level input current, low-level output current. So we can look at our data sheets and see if we can find that. Let me pop up the data sheet. Oops, wrong thing, Rich. So I need to go to Blackboard. And y'all have the data sheet for a 7404, right? $7,400. Which data sheet you got? $7,400. I'll bring that one up. Dang it. And if you don't have it, you can't find it, you can log into Blackboard. They should all be up there. I need to go back and reset that because we got two people that's absent. So I'm just going to draw the totem pole output. So we got a pull-up resistor right here, and we got a diode right here, and then we got another transistor right here. And then then my output is taken right there. Here's my common. And what we're going to do is to demonstrate this, we're going to run it into two resistors. Okay. They're stacked on top of each other. Huh? No, this is the output. No, this is the load. This is the output of the gate. So this is the output of the gate. So we call it a totem pole output because the two transistors are basically what? Stacked on top of each other, like a totem pole. Totem pole, of course, you got faces on top of there, and that's why it got the name. No, that's my load. This is I'm using that. We're gonna hook this up to something, but that something is gonna simulate this guy right here. Two resistors like that, and we're gonna have one connected up here to plus 5 volts, and then this is common. Okay, so if this transistor right here turns on, this guy right here is going to be what? Off. Current flow is going to be what? It's going to come. It's looking. So I'm looking for current flow. So if it's looking for current flow, right? You understand? Then it's got current flows from negative to positive, right? You understand? So here's my negative. Here's my positive. Current flow is out of the gate, comes up, and goes up to plus 5 volts. So current flow is out of the gate. So a low current flow is out of the gate. Y'all follow this so far? Okay, So when this guy right here, we get current flow, right? You understand? This guy right here is on. This guy right here would be what? Off. Right? Here's plus 5 volts right there. So current flow is not going to be from 5 volts to 5 volts. Current flow is going to be what? From here, right? Okay. So here we come up here. So current flow is going to be into the gate. So relative to what we're talking about, current flows into the gate, this is what they're going to mark. This is why this was marked negative. So your sourcing current is going to be marked negative and your sinking current is going to be positive. Because current flow into the gate would be negative current flow, right? Current flow out would be, that makes sense? So when we look at our data sheet, all your sourcing currents are going to be what? Negative. So it says that 400 microamps. So this guy can source only 400 microamps. Is that better? Because y'all got it. So data sheets, notice they don't use and data sheets do not use legal engineer notation. And that's just something you have to get used to. So here, they're using nothing but what? Milliamps. So 0.4 milliamps would be 400 microamps. Y'all understand that? That makes sense. So now you know why it's negative, because it's flowing into the what? Into the gate. So the maximum current I can get out of this guy's sourcing is all I can do is get out 400 microamps. That's it. So if I try to make it run a load that needs more than 400 microamps, then the output is not guaranteed anymore. How much can this guy sink? So it can source 400 microamps. It can sink what? 16 milliamps. 16 milliamps is enough to turn on an LED. I couldn't turn on an LED with 400 microamps. So if we're going to make the output of this gate do work, we're going to have to come up and figure out how we can hook up our loads to sync, right? That makes sense? Only 400 microamps. Why 400 microamps, guys? Because we got a resistor up there to prevent this thing from burning up, right? You understand? So when I look at my output, so we output through this dang resistor right there. Now, why do we do that? Because if I put this thing out here and put this thing and somebody came up here and grounded that output just for troubleshooting, it would pop that out a transistor just like that, because we'd create a short circuit. So what it does, it allows us to, for troubleshooting, we can literally come up and connect that thing to a zero right there and not burn up the gate. Right? You understand? So I could literally take a piece of wire and touch it to the output of that gate and figure out what's going on down here. And that's what that pulsar probe does. So it allows us to use a pulsar probe. The pulse can pulse this thing down to zero, and it don't hurt the gate because of that pull-up resistor up there. So we output through a resistor, and since I output through a resistor, when I source, we cannot get all that. But when I hook this sucker to ground right here, or common, it's not going through any resistor. So that means that's why we can sync. These guys can sync more than they can source. 16 milliamps. This guy can sync 16 milliamps and still guarantee my output would not be above what? Like, we got to look at the output first. And then what the maximum temperature we should operate this thing is at 70 degrees centigrade. How hot is that, guys? No, Celsius is, oh, it's lower. So freezing, what's freezing on the Fahrenheit scale? 32. What's boiling at sea level? 212. What's freezing on the Celsius scale? 0. And what's boiling? 175. Guys, y'all gonna need to know this because we're in an environment now where we have a lot of German companies here. And them suckers don't deal with what we call the English standard of measurement, right? They deal with what? The metric system. So we know that freezing in Fahrenheit, I don't know how they came up with that, guys. I mean, that's the weirdest scale I ever seen. How did they come up with 32 for freezing and 212 for boiling? Anybody know that? We might look it up. I have no idea. So on the Fahrenheit scale, 32 is what? Freezing, and 212 is boiling. On the Celsius scale, 0 is freezing, and 100 is boiling. Don't that make sense? So how did they come up with the Fahrenheit scale? 212. I don't know. 32. I don't know. This guy makes so much sense, right? So what we do is, if you did all the calculations, you'd find out that for every 5 marks on this scale, up here there's 8 marks on that scale. So the conversion is 5/8 or 8/5. So if I'm going from a 70 degrees centigrade or Celsius, the first thing I would do is I would multiply it to the bigger scale. I'd multiply it by 8/5. What would that give me? So all your data sheets, guys, by the way, are going to use the Celsius scale. So they went over to the international standard a long time ago. 5/8. It's 5/8. I'm sorry, 8/5. So 5/8 if we're going down, 8/5 if we're going up. No, but then we got to compensate for the 32 degrees. So the way you would do it is close. If I'm a calculator. So 8 divided by 5, which is 1.8. A lot of people learn, 1.6. And then I'd multiply that times what? 70. And then I'd come up here and I'd add 32. So it's 144 degrees. And why did we add 132? Because one of them's 0, right? You understand? And one of them 32 is freezing. So the 5/8 would be if we lined the 32 up with a 0. So it's 32 degrees higher. So you have to add 32 degrees. So what you would do to go from Fahrenheit to Celsius is the first thing I would do is I would subtract the 32 degrees, and that would put them on 0 together, right? You understand? And then I would multiply it times 5/8. It'd be 70 degrees. So 144 degrees, these guys say they can maintain what I'm working in if I'm running in an ambient temperature of 70 degrees centigrade, which would be 144 degrees on the Fahrenheit scale. Free air It's called the ambient. A lot of them will call it the ambient temperature. You know what ambient means? Or the surrounding temperature. Not room temperature, it's the surrounding temperature. It's whatever surrounding the device that it's running in. And that's why they call it TA. Now this is why we use 2.4, because it says V out high. Y'all see VOH? V out high says it's going to be a minimum of what? 2.4. So the guaranteed minimum, if I'm outputting high and I'm pulling less than 400 microamps, is guaranteed to be at least 2.4 volts. So if the output is guaranteed to be 2.4 volts, that's what I'm going to look for. Even though the input accepts 2 volts, we're going to look for 2.4 volts, because if you don't get at least 2.4 volts, it means something is going wrong, right? You understand that? Yes or no? So there is a 400 millivolt, there's a 400 millivolt safety margin depending on what the input is accepted and what the output guarantees. So the output guarantees 2.4 volts for a high. It's guaranteed. The input says, I'm going to accept 2. So that means as long as we don't overload this sucker, these guys are going to work. If I try to get more than 400 microamps out of this thing, it means the 2.4 volts is not guaranteed anymore, right? You understand that? Yes or no? I'll take a break.